Well, hello, this is Matt Roscoe again from our course M573, Teaching Geometry for Teachers with a content lecture for week 2. We're going to take a look today at synthetic geometry. So I'd like to just basically introduce what synthetic geometry is, what's meant by the term, and then talk about how I guess we as a course will proceed. It's a little sticky because of course we know some geometry already. And then I'd like to use our place to start and I guess springboard from there to some examples of synthetic geometry or applications of synthetic geometry. So what is synthetic geometry? It's sometimes called axiomatic or pure geometry, and it's the study of shape using an axiomatic method that begins with a set of givens. Usually we call those axioms or postulates, and builds results. So those would be theorems or special cases of theorems, which are called corollaries, using only the tools of logic and the tools to draw points, lines, and circles. So compass and straight edge constructions are allowed here. So really this is proof-based geometry, the thing that most of us probably had in high school, if we're of a certain age. It is getting to be less and less popular in the high school, I guess, experience of students. But definitely this is where proof is front and center, I guess, in the teaching of mathematics. Oftentimes people say that geometry, one of the important aspects of geometry is it's where students get to learn about proof, and oftentimes it is these proofs that are actually the things that we are assessing in our courses, whether or not they can prove something or not. So in a traditional synthetic geometry course, we'd start with basic assumptions, that'd be axioms and postulates, and build up new results using logic and constructions. But since we all teach geometry and have some familiarity with these basic results, I'm going to assume that you're aware of the following list of definitions, properties, angles, measures, postulates, and theorems, and we'll build from there. So in other words, let's all sort of agree that these, I guess, the following lists form sort of the givens, the things that we know. I mean, I'd just like to, for a second, take a chance to reminisce about when I taught geometry in high school, which has now been almost 20 years. When I did this, I thought, the best way to do this is to sort of put the things that we prove up on the wall as we sort of went through the course, and tell the students that, look, these are the only things we can rely on. So what I did is I got, big sheets of I guess butcher block paper, newspaper print, I guess is what we called it back then. And each time we proved a new theorem, what we did is then we put it up on the wall, and gradually sort of the wall around my classroom, and sort of hanging from almost the ceiling, was filled with theorems that we had proved across the semester, things that we could rely upon. And I made those fully available to them. They just sat up on the wall, even during assessment settings. And so there was no need for them to have like a cheat sheet or a special, I guess, one page of notes with all the theorems on it that we'd proven. It just sort of lived in our classroom. And I found that students, at first really relied upon those things, and as the semester went on, of course, they got used to certain theorems and looked at them less and less on the wall. But I thought it was a nice way to go. You're going to see in one of your readings for the week this idea of proof blocks, which to me is essentially the same approach. It's just that the blocks themselves are sort of cards, and students are given these cards and asked to use the blocks in diagrams to create diagrams of proofs. And I'll do some diagramming of proof today as well. So yeah, just a little aside, little commentary there. So here we go. Place to start. We all should know the definitions of a line, a segment, and array. These are all determined by 2 points, so we can create them as needed. We also should know, I guess, the definitions of triangles, either scalene, isosceles, or equilateral. That would be definitions by no sides congruent, at least 2 or 3 sides congruent, acute, right, or obtuse, so all angles less than 90, 190 angle, one, I guess, angle greater than 90. And then quadrilaterals, we already went over those in the last lecture, so be aware of those definitions. And we also went over the definition of a circle, but its definition is basically a collection of points equidistant from another point, that point that they're all equidistant from, we call the center. So in other words, anytime we have a circle, we can find segments of equal length. Those things are called radii by choosing any point on the circle and connecting it to the center. Constructions, we should be able to construct points at intersections. We should be able to construct rays, lines, and segments. I'm going to leave out, congruent angles or parallel lines for now, but of course those are things that sometimes show up in geometry courses in high school. Let's go ahead and talk about properties. So reflexivity is this idea that any number or any segment is congruent to itself. So sometimes we use a segment in two different triangles. If it's in two different triangles, and we use reflexivity to let it belong, be congruent to itself if it's a shared segment. And then transitivity is this idea that if A is congruent to B and B is congruent to C, then A is congruent to C. What about angle measures? So we should all be aware that a full rotation about a point measures 360 degrees, straight angle measures 180, a right angle measures 90. The exterior angle sum of a polygon. So this is this idea that if we walk around a polygon and we scribe the exterior angles or we add together the exterior angles as we walk around a polygon. Well, walking around a polygon gets you back to where you started with exactly one rotation. So the exterior angles of a polygon sum to 360 degrees, no matter what type of polygon it is. That might be familiar or unfamiliar to some of you, but try it out. If you walk around a triangle, you have these three exterior angles that you would put together, and they would add to 360. That basically becomes the basis for the triangle angle sum theorem. That's the way oftentimes we prove triangle angle sum. So triangle angle sum, of course, 180 degrees for the interior angles of a triangle. And then that can be generalized by just triangulating any polygon. So for example, a quadrilateral sums to 360. Any pentagon will sum to, well, there's three triangles in there, so that'll be 540. Any hexagon will be another 180, so that would be 720, and so on. So the algebraic expression is that if a polygon has n sides, then n minus 2 times 180 is what the interior angles sum to. So we'll assume that you know the polygon angle sum theorem, and then some postulates and theorems. Let's assume all of the triangle congruence criteria. So side, 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 angle, angle, and angle, angle, side, triangle congruence. And then of course, usually when we prove triangle congruence, we use CPCTC to pick off the pieces that we need. And that just basically says that once we have triangle congruence, using usually the minimal conditions, which are three elements, either three sides, side, angle, or angle, angle, side, then we get all the rest of the angles and the rest of the sides come along for the ride in congruence. So we get three other sets of sides and angles. So that's what we invoke once we have triangles congruent as CPCTC. Let's assume we know about vertical angles. So that's when two lines intersect. The vertical angles are congruent, and let's assume that we know the idea of parallel lines cut by a transversal, that corresponding angles are congruent. Usually this gets developed into all kinds of different ways of proving parallelity. So for example, alternate interior angles or alternate exterior angles, or supplementary interior angles. Anyway, so there are quite a few different ways that this breaks out, but let's just stick with the basic. We know corresponding angles. When they are congruent, the lines are parallel, and the converse is true here too. When the lines are parallel, then corresponding angles are congruent. So that's a place to start, I guess. Let's go ahead and dive into an example. So let's do something simple, and then we'll follow by something sort of medium, I guess, in complexity, and then end with something that's fairly complicated. So let's prove a simple statement that the base angles of an isosceles triangle are congruent, just as a starting place. So I'm going to switch over to my Elmo cam.